Okay, so welcome back. Nice to finally meet all of you again, and to see you in person. I can't see your faces because of the masks, but I get the idea. Um, and this is our fifth lecture, and this is lecture 5.1 in particular, where we're going to continue our study of this single neuron model with relation to supervised machine learning. Now, if you have cloned my repository and have the latest version of it, you will see a bunch of folders and you should open up lecture 5. Okay, that's all the content that we'll be working with today is in there. Now, if for whatever reason you haven't installed VS Code and you don't know how to access those notebooks that are there, I have recently started to do something different, and I'm going to update all of my notebooks to include this functionality, where so for example, lecture 5.1, that's what we're doing. You see my notebook here on my GitHub repository, but now there's a link right here. It says open in Colab. If you click that link, it'll take you to Google Colab, and you can run the code virtually, right? This is a free service. It's fast, it's awesome, it's really simple to use. You just have to press Shift Enter. It works just like a Jupyter notebook. Okay, and you can change your theme to be light colored, dark colored, doesn't matter. But yes, so all of you will have access to that at least, even if you don't yet know how to clone my repositories. Okay. And I encourage you to look at my code and make the same links, right? It's not that hard to do. If you have a GitHub repository, you can make a link to open up that notebook in Google Colab, and it makes it easier for others to use your code, right? So if like a potential employer wants to run your code without installing anything, you can just make a link and let them play with what you've written. And the syntax to do that, so here is the actual Jupyter notebook that I pushed to that repo. The syntax to do that can be found by double-clicking the markdown cell, and you'll see exactly what I did, right? I provided it the link of that, like the web URL for that specific page on GitHub. And so there's no, here's the link right here. And then before, this is a special like badge to give it to show that button to click on. Okay, so you just have to double click the markdown, you'll see it. So basically what you can do is once you have your GitHub repository set up, you can just copy what I did here and just put your URL in there, and then you'll have a button too. The only thing that you have to be careful about is when you have data sets that you're working with. So for now, I'm only using libraries to import the data and not reading from my machine, because when you have a notebook on Google Colab, there's like a few steps that you need to do to put data on there. It's not as simple as just running the code. So you'll notice that in today's lecture, for example, I'm using the iris data set again, but this time I use a library to load it instead of reading it from disk, like on my machine. And so, but I'll make a video or describe in class one day how to host data on Colab. Okay. All right, so yeah. No, it won't change my code. It's like on your account once you click on that. Okay, so now to the main topic of part 1 of this lecture. So we have learned that the single neuron model, which is shown, where is it? Here. We've learned that this can be used for both classification and regression, right? The classification example that we gave was this perceptron single neuron, and the regression was linear regression, right? And the differences between those two neurons, those two models, there's only really, besides being like classification and regression, but the model itself, the neuron model that we're like imagining in our brain, right? The only thing that differed between those two models was what? The activation function and the cost function. Those are the only two things that really differed between them. Even when we trained them, right, with a stochastic gradient descent for linear regression and the perceptron update rule for the perceptron, the training was the same. The partial derivatives of the weight and bias were the same. Even though the sign function for the perceptron is not differentiable, it turns out that that update is a discrete approximation to what the derivative should be. So it actually turns out to be the same, okay? Now, given that, we're gonna extend this one more time to another type of supervised learning, another type of classification called logistic regression. Now, I should note, there actually is one other type of single neuron model for support vector machines, but I will not be covering that because we need to move on to multi-layer neurons. But just know that that exists, and we'll actually talk about support vector machines later in the semester. And okay, on to logistic regression. Now, logistic regression, the name is kind of confusing because it says regression in it. But logistic regression is a classifier technique. It's used for classification. And it differs from something like the perceptron in that the predicted outputs, the y hat of our model, right? The predicted output of the single neuron in this case is not going to be a 0 or 1, or a -1 and 1, I'm sorry, for the perceptron. It's going to be a probability. So why would we want to predict a probability instead of a label, right? And when I say probability, I mean a likelihood of being a label, the probability of being a label. So in order to motivate this, I'm going to run this code here. So as always, there are the three that you will most likely always import, Matplotlib, NumPy, and pandas. And then I've found myself always importing Seaborn for styling my plots. And then we have this fancy MLX10 plotting function here for plotting decision regions to view the regions of space that our classifier says is this or that. Okay? I set my theme, and then this is new to all of you. I use Seaborn to load the iris dataset. Seaborn has several data sets that are really fun to play with, the iris being one of them. There's also the penguins data set that I've given to you in the past. And I'm using that to load it in so that I can host this on Google Colab and not worry about any file saving. Like, and now, after doing that, I make sub data frames. So this code here is making a Setosa data frame, which consists of all the rows and columns that belong to Setosa. Okay. Notice the syntax. The original data frame is called df. So df brackets df.species, so that's a column, right? So wherever the column equals to Setosa is true, it's going to take all those rows and turn it into a data frame. I do the same thing for the Versailles color, the same thing for Virginica. All right. So next up, I use the Matplotlib subplots function or method. Now, I was actually reading Matplotlib documentation the other week, and I've been using plt.plot for all my single plots. They actually mention in their documentation that the preferred way should be subplots, even if you're plotting one figure. I don't know how I feel about that. I'm going to try to start doing that, but I don't know. I should just note that it was definitely in the documentation and I missed it in the past. So how does this work? Well, whenever you, back to this subplots method, this is going to return a tuple, fig, and then your axis, right? And you pass in the subplots, the dimensions of your figure. So it's going to be a 1x2 figure. So I'll have two figures in the columns. And then I set my fig size to this. And that's the fig size of like the super fig, like the bigger fig. So on the first figure, I'm going to scatter setosa sepal length, setosa sepal width, give it color red, label it setosa. And then on that first figure, I'm going to also scatter versi color, sepal length, versi color, sepal width. So same measurements, right? I color those magenta, give it label versi color. I set my X and Y labels. Notice that the Y label and X label methods here, there's a set underscore before it. That's because that is the syntax for subplots. Right? Legend is the same. And then set underscore title, again, that's because we're using subplots. Okay. So this is our first figure. And then our second figure is going to be versi color, petal length, versi color, sepal length. And then Virginica, petal length, Virginica, sepal length. Same thing, so let's just run this and see what happens. Okay, so there it goes. Now, okay. Notice on the left-hand side, we have sepal width and sepal length measurements for the setosa species and the versicolor species. We did find a classifier for that left figure, right? The perceptron. When we did the perceptron, those are the exact measurements and species that we used, and that perceptron clearly found a line that split that data into two regions of space, right? But that was because there is a line that separates it, right? Like if you look really closely, there is a line, and we've seen it before, right? It separates that data. But what about here? On the right-hand side, for this, the versicolor and Virginica species with those two measurements, there is no line that separates that data, right? No matter what line you pick, a line trying to split that data, there's always going to be overlapping of species in a region, right? However, looking at it and focusing on the petal length, right? If I were to draw a vertical line at like say 4.7 or something, right? If there was like a vertical line like here, the majority of Virginica flowers would be to the right of that vertical line, the majority of them. And the majority of the versicolors would be on the left, right? But imagine like you had a line splitting that, right? And you sampled from to the right of that line. And you just sampled, like picked a point arbitrarily. I just kind of picked out. You would have a higher probability of being a Virginica flower, right? And on the left-hand side of that line, your probability of being versicolor should be higher. So maybe instead of using both these measurements, maybe let's focus in on just the petal length as our measurement to consider. And then we have two different species. Maybe we can somehow find a separator based off of that one measurement that predicts the probability of being this or that. So in this case, for versicolor, maybe we could give the label 0. And Virginica give the label 1, right? So those would be like the set in stone labels. And probabilities, as you know, are between the values 0 and 1, right? So if we predict out a probability and that value is higher or closer to 1, then we would hope that the likelihood of it being Virginica is very high, right? In the lower probability we predict, it's almost like we're saying the likelihood that it's a versicolor is very high, right? So, oh, I have like a little question here for you guys to think about. Here on the right-hand side, if we tried to use the perceptron on that data, how would the overlapping points, there's no clearly separating line, right? How would that affect the training of the perceptron? Think about what the perceptron predicts. It's a hard -1 or 1, right? And if there's always overlap, it's going to be fixing fixing completely, right? Which would mess up the next prediction because there's overlap. If there's too much of a jump, we need a smooth transition so that those hard jumps in training, because again, when we update the weight and bias with the perceptron update rule, we're trying to fix it, right? But there's no way to fix it there. It's always going to be jumping around. So actually, the perceptron wouldn't converge to anything there. But this is why we're transitioning to a softer approach than this hard jump, which is with the probability prediction. Okay. So let's look at this plot here. So here I'm using regular scatter. There's no subplots here. And I'm scattering versicolor petal length, which was the X measurement up here on the right-hand figure. And I'm going to give those labels 0. So all of those are labeled 0. And then Virginica, scatter petal length, but now the Y values would be 1 for each of those values. And then I make a vertical line just to kind of illustrate a point. And let's just look at that. Okay. So here we see that we're only focusing in on one measurement now instead of the 2. Right? That's our X value, and our Y value is either 0 or 1. Right? The Virginicas have label 1, versicolor have label 0. And notice, like I was saying earlier, the majority of versicolor might fall to the left of that line. Right? Like if you sample from the left of it, you're most likely going to get a versicolor. If you sample from the right, you're most likely going to get a Virginica. Okay? So we have to consider now how we could model this with a single neuron. Well, we have a single input in this case, right? Just petal length, right? Pre-activation, that always stays the same. But now we have to figure out like what our activation function should be. And the function that we're going to choose is something called the sigmoid function, sometimes called the logistic function. This function is 1 over 1 plus exponential e to the power negative z, if z is your input. This is a differentiable function, which is good. We like differentiable activation functions because it makes gradient descent like viable as a choice to optimize whatever cost function that we pick. Okay? So let's take a look at the shape of the sigmoid function. Okay, and it has range between 0 and 1. So it's a candidate for a probability, right? If its range is between 0 and 1, that's good. So I define my sigmoid function. I'm going to use subplots again, 1 by 2. So this first code here is simply the plot above, just now in subplots form. Okay. And this second plot here is, well, I make a domain using NumPy's linspace method. And then I plot the sigmoid values on that domain. Okay. So let's see what this looks like. Look at that. Look at how the shape of the sigmoid function is modeling the separation of those two different classes, right? So this seems like a good activation function for our single neuron. As the value z increases, right? At some threshold, the sigmoid function starts, or the post-activation value, the output, starts rising. And at some point, the likelihood of it being green is high, right? So we need to now, well, not maybe I'm wording it bad, like just looking at it, if we can find a mapping from petal length to z that will match up these two graphs, we are good. And we have a potential classifier to deal with. So, oh, well, in order to find those weights and biases that will map the input to the appropriate domain for the sigmoid function, we need a loss function, right? In order to train anything, we also need that loss function or the cost function, right? That's the thing that we optimize. So what's the cost function that we're going to use, or loss function? Now, there's going to be a lot of math going forward in my notebook, but we're going to talk our way through it, and I might have to pause the recording, pull up this projector, and do some math in front of you. Okay, so we'll see. I'll try to feel you out as we're talking about it. Okay, so going back to the problem at hand, we have two different species, and we have a probability of one versus the other. This is very similar to just flipping a coin, right? It's like it's a binary probability. It's like heads or tails, right? And moreover, what is the model doing for us? Like we predict out a probability, but what does that prediction depend on, right? Like if we look at the model here, this is going to be a probability. It depends on something. It depends on the input, right? So what we really have is a conditional probability. So let's talk about this formula in front of us. The probability of yi, which that's the correct label, given xi. Okay. Now this is going to be equal to the piecewise function y hat if y is 1. And then if y hat is a probability, what is 1 minus y hat? It's the probability of the complement, right? So y hat if y is 1, 1 minus y hat if y is 0. So it's almost like, so 1 would be heads, 0 would be tails, right? So this probability depends on the y hat that we spit out from the neuron. So the weights and biases determine that thing, right? Like once we set weight and bias in stone, then we have a probability always, right? It's like almost like a biased coin towards one of them probably, right? But once we change those, we get a different probability and a different conditional probability. So, okay, let's look at, oh, I should probably read my slide or my notebook more. We wish to maximize this probability over all training examples. Since this quantity is largest when our predicted probabilities are close approximations to the true 0-1 labels. So let's think about that. What does that mean, right? So suppose that we were predicting really good, right? Suppose we had trained our weights and biases and we're doing really well. Then this y hat, right? If we're doing well, it should be a good approximation to y. It'll be closer to y. So if we're doing really well, if we input one example here and suppose the label was 1, then this would be a 1 or close to 1, like 0.98 or something. Again, if our model's trained well and we pass in a pair where the label is 0, then our y hat would be small, right? So then this would be like 1 minus 0.002, right? So if we're doing well, that probability is close to 1, right? It returns a value close to 1, I mean, right? Does that make sense? So if we're doing well, we have a value close to 1 for a given input, and if we sum over all training examples, and we're always doing well, it's going to be a lot of things close to 1, it's going to sum high. If we're doing bad, on the other hand, and we're not ever really hitting it, the correct label, or getting close to the correct label, then in that case, if our model is doing bad, this y hat, if it's a 1, then we would predict like 0.001. That would be the value here, right? And if our model is bad still, and we observe a training instance with label 0, then y hat would be close to 1. And then this value 1 minus y hat would be small. So you see, if our model is bad, we're summing a lot of things that are close to 0 over all the training examples. If our model is good, we're summing things that are close to 1. So it makes sense that we would want to find W and B that maximize this conditional probability. Because if we find the best possible W and B, that means that we're always close, right? So that's what we want to do. We want to maximize this. And this probability depends on the choice of W and B at hand, right? So now, before we actually try to optimize this thing, we need to work out a differentiable form of those conditional probabilities. Right now, it's this piecewise function, right? We need to modify it to be so that we can take the derivative of it, right? So notice by this famous Bernoulli equation that conditional probabilities, right, or probabilities in like the binary case, there's a very simple formula for it. And that formula is typically written, it's like p to the power 1 minus p or whatever. Like it's probability and it's complement, and there's like these powers. Well, in our form, we know that the y hat is the probability, 1 minus y hat is the complement's probability. So this is the form of this conditional probability just by applying Bernoulli's equation, which I should have just stuck in here so that we could see. Literally, that's all it is plugging in p and then 1 minus p. So now this looks a little bit better, but it's still messy. And we're going to modify it again. So if this conditional probability is equal to this product and for each of these powers, then we can take the log on both sides of the equation, right? That's valid. So we take the log on both sides, and we get log of p is equal to log of this thing here, right? And then we can use log rules. Like we all know these log rules for like sums, right? So notice the log of the product is the sum of the logs, and then the exponents become the coefficients. Do y'all see that? How it simplifies? I dropped the superscript I because it was getting too messy to fit in the notebook. But really, we're looking at a given instance each time, right? Which is xi, yi, and yi hat. Okay. So we originally wanted to maximize the sum of these probabilities, right? But now we have log of these things. Well, because the log function is non-decreasing, right? It's increasing. Maximizing the original function is equivalent to maximizing the log of that function because it's increasing. So that's what we're going to do instead. That's not what we're going to do, but that's what we're thinking about, right? We're transitioning from maximizing the sum over these p to maximizing the log of those p, right? Which is this side here for each instance of training. Okay. Now, we could technically use a technique called gradient ascent to solve this problem, right? Instead of gradient descent, gradient ascent, meaning we would go in the direction of the gradient, not in the opposite direction. We would find a local max. However, just so that we stay consistent, we're going to transform this maximization problem into a minimization problem so that we can stay with gradient descent. And the way that we do that is we just tack on a minus sign on it. So maximizing log p is the same thing as minimizing negative log p. And again, the true loss function over all training examples is the sum of these values for each training instance, right? So it looks like this. This here is called the binary cross entropy loss function. The name entropy is related to several things in machine learning, but also it comes from physics as well. And this is related to problems in physics, and I'll maybe even include a link for this on my GitHub page. Okay. So we have a activation function, the sigmoid function, and we have a loss function, the binary cross entropy loss. We have our model ready. So here is the logistic regression single neuron model. Okay. There shouldn't be double equals right here. It should just be equals. I need to fix that. But this is it. Okay. So now we need to find the gradient of that cost function, right? Now, as before, with both of the previous single neuron models, we didn't really care to calculate the full gradient, which you do by finding the partials with respect to each of the training pieces, right? And then summing them all together to get your gradient. All we need to really do is figure out how to calculate the gradient for one single training instance, right? One instance. If we can find the gradient of C with respect to the weights and the biases for that one instance, then we can use stochastic gradient descent and refine, okay? So that's what we're gonna do. So for a given single instance, our cost function in the current model, we have one weight and one bias, looks like this. It's precisely this, right? Now, when considering this equation, it's important to remember that y hat really is a composite function, right? Y hat is equal to sigmoid of the pre-activation, right? And z is itself a linear function of w and b, right? So noting that, and because we're going to have to take derivatives, I'd like to just tell you that the derivative of the sigmoid function has a very nice closed form. Its derivative of sigmoid is equal to sigmoid times 1 minus sigmoid. And it's actually not that bad to derive. I get my calculus 1 students to do that, right? So I encourage you to derive it just to verify for yourself. So now we have these two equations, we can get started. So here's our cost function right here. There's two pieces to it, right? There's this first piece and this second piece, right? Now, to kind of keep things clean, I'm going to take the derivative with respect to W1 on the first piece here, and then take the derivative with respect to W1 on the second piece. And because the derivative is a linear map, for any of you that are CAM students, that's important to know. The derivative is a linear map. The derivative of the sum is the sum of the derivatives, right? So I'm going to use that property to kind of save room. And this is something that you can do in your other classes when you're writing like LaTeX for like huge, like long equations. You can split things up and do it in pieces. So here's the derivative of the first piece with respect to W1, this piece right here. Okay. So I'm going to apply this operator to both sides. I mean, to this first piece, and then I get, well, first, I'm going to note that y hat of I is really sigmoid applied to W1 times xi plus b, right? That's what y hat is. Noting that, I take the derivative of the log first. So what's going on here? We have, what's happening here? Well, it's simple, right? Derivative of log, if we have like natural log, right? It's just 1 over x, right? It's 1 over f of x, right? So notice it's negative y hat on top. And then in the numerator, I mean the denominator, I'm sorry. In the denominator of this first ratio is precisely the function inside. So using the chain rule, derivative of log, which is that right here, this first piece, times the derivative of the inside. It's the chain rule, right? And I wrote it as sigmoid of W1 xi plus b, just so you can see how easy it is to take the derivative of that thing, right? You can see that what's going on. So then the derivative of the sigmoid function is sigmoid times 1 minus sigmoid, right? So sigmoid times 1 minus sigmoid, that's right here, times the derivative of the inside, chain rule again, right? If you think this is bad, wait till we get to next lecture, when we have multi-layered neural networks. So chain rule on the log, chain rule on the sigmoid, and finally we arrive at the derivative of z with respect to W1, which is just what? Xi, right? That's the coefficient of W. So also notice that this sigmoid and this sigmoid divide out, right? They divide out, so that ratio goes away. You're left with negative yi times 1 minus sigmoid times xi, the coefficient of W. So this is what that piece becomes. Am I going too fast? Yeah. I spent a lot of time on this one for you guys, so hopefully it's like clear. Okay, so now we have to do the same thing with the second part. I apply this operator, the derivative on the second piece. All right, so again, this is just like a constant, the negative 1 minus yi, divided by inside of the log, right? That's the derivative of the log, right? 1 over whatever's inside there, times the derivative of the inside, right? Yeah. A derivative of v. Yeah. So the derivative, okay, back up to here, this line here. The derivative with respect to W1 is the coefficient of W1, and that b is nothing. It's just 0. Yeah. And we'll get to that in a moment. We have to take the derivative with respect to the bias as well. But first, let's get this second piece out of the way. So then, what was I saying? So negative 1 minus yi over the inside of the log times the derivative of the inside becomes this, and then times the derivative of the inside of the sigmoid, right? Because I apply dw to this right here, the derivative of 1 is 0, minus the derivative of sigmoid. So it'll be minus sigmoid times 1 minus sigmoid, times the derivative of the inside. So the chain rule is happening twice, on the log and then on the sigmoid. And then the coefficient of W1 here is again x, right? So we simplify this all out and it becomes this. So now all we have to do is add this piece, and that will be the derivative of the cost function with respect to W1, because again, the derivative is a linear map. So we do that. Here's the first piece. Now I'm using the y hat notation again. Now we understand what that is. So here's first piece plus the derivative of the second piece. I factor out the x value, and then I get this. I collect my like terms. I distribute in. I get this. But then notice when I do that, I have negative y times y hat plus y times y hat right there. Those go to 0. So we're just left with y hat minus y times x. Now, if we think about this in terms of the bias and just look back up at these terms here, everything will be the same except for right here. If we were taking the derivative with respect to the bias, everything except for this part right here would be the same. And then here we would take the derivative with respect to the bias, and this would be a 1. Right, so there'd be a 1 right there. And then the same thing here, that would be a 1. So we put them together and we get the derivative with respect to the bias is just that. What does that look like to you? Those partial derivatives. It should look very familiar. It looks, let's see if I might. Let me find it real fast. The perceptron partial, approximate partial was this with W, and the bias was this. That was the partial. Ignore the 1/2, the part next to the 1/2, right? Those are like the approximate partial derivatives with respect to the weights and biases. And the same thing for, I think it was, let's see, this lecture maybe. Where is it? Look right here with linear regression. Look at the partials with respect to the weights and the bias. It's the same. That means that the single neuron class that we, like the object, the Python object, that we made for the linear regression model and the perceptron and logistic regression, the update rules are the same for all three models, right? The stochastic gradient descent can be implemented the same. So noting that, I make a single neuron object again. And now there's a few changes, I think, from when I did this with linear regression, maybe not. So I initialize it with an activation function and a cost function. The reason why I choose these to be passed into the init method, or the initialization of my single neuron object, is that that's all that defines the differences between the models. And I want it to be as general as possible. Okay, so train, we've gone over this before in a previous class. We pass in features, labels, a learning rate, number of epochs. And then the update is the same regardless of whatever model we're doing. Okay, then I have predict using my activation function. And then I added this business here, these plot methods to the class, because I was tired of typing all that plotting code over and over again, like in the previous lectures. And again, I've mentioned this before. If you're ever typing code the exact same more than twice, you're not coding right. You're not being an efficient programmer. So that's all that's getting rid of there. All right. So there's my single neuron model. I ran that cell. Now, next, I define my cross entropy loss exactly as it appears. And then I already defined sigmoid above, right? I instantiate a new single neuron and I pass it sigmoid and cross entropy, which means that this is a logistic regression neuron. Then I grab all of the X measurements for the Versailles color and Virginica flowers, which are 50 on. I already know that. Now, because this is a single measurement, I have to reshape the thing, right? So I reshape this to be a column vector representation. And then I use the NumPy where method to look through the species. And whenever it says Versailles color, I give it the label 0. And if else, I give it label 1. Okay. So that's my Y. And then I train. I call my train method. I happen to do 10,000 epochs. I don't know why that's so big, but whatever. And yeah, that was, there it goes. Okay, it's trained. All right, let's call the plot cost function method now. Notice I don't have to type a bunch of stuff anymore to look at the cost function. It looks like it's learning, right? We're doing things right. Okay, so now we can predict, we can make a plot of our predictions. Okay, if you remember up here, this is our data plot, and this is the type of line or curve that we're going to spit out, and we want it to overlay over that data to indicate the changing probability as you get higher and higher on the petal length axis. Okay, so all right, make a figure, set X limits. All of this is the same as above. And then down here, I make a domain with lens space. And then I call my predict method on that domain. But again, I have to reshape it because it's a single column, right? I have to make it look like a column vector to plot it. If I run that, there we go. It looks pretty good, right? It looks pretty good. In the way that you would use this to make actual label predictions in practice is something like label 0 if the output is less than 0.5, label 1 if the output is more than 0.5, right? So somewhere around here would be the cutoff for the predictions. But because we're predicting probabilities, you don't have to do that. You can sample from 2 different classes with a given probability, right? So, like for example, I'm going to add a code cell right here. What is it? Node dot predict. So those are all of the predictions for the given features. And you can see that all of these are these are the bigger ones, right? The exponent's larger, I mean smaller over here. All right, so let's look at a classification error. And so we haven't really done this before. No, I think we have, but again, so what's going on here? We're summing, so inside these brackets here, we have our prediction and our label, right? For a given instance. Now, the value here is 1 whenever they don't equal, and 0 otherwise. So we're summing all the times we don't predict the correct thing. Okay. And the way that we're going to do this, so why did I not? So those are predictions. Or yeah, these are the probability predictions. So I'm going to say classification error, I don't know why I gave it that name, is equal to mp dot rent, round to the nearest integer. So if you're below 0.5, it rounds to 0. If you're above 0.5, it rounds to 1. Okay. So round to the nearest integer, everything in this array here. And then after doing that, not equals to y is going to make a Boolean list of true and false values. Right? Like I can actually show you. Let me do that here. See? And then because it's a Boolean list, it's a Boolean numpy in the array. I can convert it to type int by just doing the dot as type method. So the falses would be 0s, the trues would be 1s. And then I print the sum of all the 1s, right? Because that's what's going on in here, divided by the length of y. Let's see what it is. 0.07 of all. Right? So it's the number of misclassifications divided by the total number of points. Right? Next, I'm going to call my plot decision boundary method that I put into the class. Look at that. That's nice. Okay. So now this was done with a single measurement, right? We just used petal length, right? Yeah. But this works for multiple inputs as well. Everything's the same. We just have to be a little bit more careful with the, no, we don't have to be more careful. Like we're just, it's the gradient with respect to the weights is the same, right? So, what do I do here? Node 2. So I make another instance of my single neuron. It is a logistic regression neuron. And then this time for my X values, I grab petal length and sepal length. So I include another measurement, right? I don't have to reshape it because it has 2 columns. I'm good to go. And Y stays the same. They have the same labels 0 and 1, okay? So then I train node 2 for 10,000 epochs using X2, the 2 measurements. All right, and then I plot my errors. It's going to take a second to train. So while that's training, you can see here what's going on. They train for the same number of epochs, right? Node 1 and node 2. So I'm plotting the node 1 cross entropy loss, and then node 2. Node 2 was taking in 2 features, right? Notice the loss for node 2. It's lower. That's good. So those 2 features, what were they? They were petal length and sepal length. Those 2 features gave the node more information about what species was what than just the single feature. In this case, sometimes you don't need extra features at all. And that can like be bad for your model. But in this case, it's good. Okay. So then let's plot our node 2 decision boundary. There it is. Notice that it's still a line, right? It's because it's a linear classifier. Even though our output is a probability using the sigmoid function, the boundaries determined are given by that pre-activation, right? So this looks nice to me, right? So I think this is a good place to stop the recording and take a break.